Section 3.2 is continuation of what we just did on 3.1, and we already did most of the work. We just didn't really finish it up because they didn't ask for it, and that's finding a relative maximum or relative minimum. If f has a relative maximum or a relative minimum at x equals c, then the critical numbers of f, then c is a critical number of f. So if you have a maximum or a minimum, it must occur at the critical numbers, and we know to find the critical numbers from the previous section. That is, either f prime of c equals 0 or f prime of c is undefined. So we work backwards. We say, okay, let's find where f prime, let's find the critical numbers, let's figure out where they equal 0 and undefined. That's how we find the critical numbers. Do the testing and figure out whether these are maximums or minimums. Page 184, I'm looking at problem number 2. So first, to find the critical numbers, I take a derivative. Set it equal to 0, it exists everywhere. So x equal a negative 4 is a critical number. Now we want to test if this critical number is a maximum or a minimum. Well, it's fairly simple. There's the derivative, there's f. If I put negative 4 there, and I pick a point to the left of negative 4, let's say negative 5. Negative 5 times 2, negative 10 plus 2 is negative. And if I pick a point to the right of negative 4, let's say 0. Put a 0 again right there. 2 times 0 is 0 plus 8 is positive. This function is decreasing, then it's increasing. That makes this a minimum. So here it says find a relative extrema. We have a minimum value of what? You take negative 4 and you plug it into the original equation. The original has a maximum or a minimum. So we have, what's f of negative 4? F of negative 4 would be, let's see, negative 4 squared plus 8 times negative 4 plus 10. That would be 16 minus 32 plus 10. 26 minus 10, we have a relative minimum of negative 6 at x equal negative 4. And when we graph those later on, we're going to put this in a graph and put everything together. If I look at number 6, the same idea applies. If I want to find whether this has a maximum or a minimum, I take a derivative, bring the power down, the 1/3 will cancel, that's x squared minus 1. Where does that equal 0? When x equal plus or minus 1. In this case, I'm testing negative 1 and positive 1. This is g prime and this is g. I pick a point to the left of negative 1, say negative 2. Negative 2 squared is 4, minus 1 is positive. A point between negative and a positive, 0. 0 minus 1 is negative. And if I pick a point to the right, say 2, 2 squared is 4, minus 1 is a positive. This function is increasing because the derivative is positive, then decreasing, then increasing. What does that mean? That means we call those L, local, a relative maximum, relative minimum. So for this problem, let me just set this up a bit better. There we go. So for this problem, we have a minimum at x equal negative 1 and an, a maximum. This is a maximum, right? We have a maximum at x equal negative 1 and a minimum at x equal 1. And if I plug this in and negative 1 in there, I'll get 1/3, negative 1/3 plus 1 is 2/3. And if I put a 1 in there, 1/3 minus 1 is negative 2/3. So this is the maximum value and this is the minimum value. Again, we're not plotting those. This is all we want. We want to find where they have a maximum or a minimum. radicals are a bit messy. If I take a derivative of this, I'll get 3 minus, bring the power down. 1/3 of 36 is 12x. Subtract 1 from the power. 1/3 minus 1 is negative 2/3. So this is 3 minus 12 over the cube root of x squared. If I get a common denominator, let me think. There are a couple of ways I could do this. Yeah, it doesn't matter. So this over 1, get a common denominator, that's 3, the cube root of x squared minus 12. So, when I want to figure out my critical numbers, these are the critical numbers, I'm going to say, where does the derivative equal 0? Where does the derivative not exist? The reason I didn't bring this up in the previous problems, this is a linear equation, this is a quadratic, they're always defined. No need to say where does it not exist if it always exists. So here, where does the derivative equal 0? Where does the top equal 0? 3 times the cube root of x squared minus 12 equals 0. When 3 times the cube root of x squared equal 12. If I divide by 3 both sides, I get a 4. And if I cube both sides, I'll get x squared to equal, that would be 64. So x would be plus or minus 8. And this derivative does not exist. A fraction does not exist when the denominator equals 0. Cube root of x squared equals 0. That's when x equal plus or minus 0 is still 0. I'm going to lift this up a bit because I need more space. So if I do my testing, I have 3 points to worry about. I have to worry about 0, an 8, and a negative 8. So when I say let's find the derivative, I need to pick a point to the left of negative 8, say negative 9. Since I am squaring this, it's going to be positive. Denominator will always be positive, so I don't have to worry about that in any of these cases. But in the top, if I am to put a negative 9 there, negative 9 squared is 81. The cube root of 81 would be, let me think, 81, 9 times 9. Okay, it's going to be easier to pick a test point of negative 27. Reason for that, if I cube root negative 27, I'll get a negative 3. Squared, that's a 9. Times 3, that's 27. 27 minus 12 is positive. If I pick a point between negative 8 and 0, negative 1, if I am to go back and put a negative 1 right there again, squared, that's a 1. That's 3 minus 12, which is negative. If I pick 1 as a test point, 1 in there, squared is 1, cube root of 1 is 1 times 3. 3 minus 12 is negative. And if I pick a point to the right of 8, let's say, again at 27, if I take the cube root of 27, that is 3, and I square it, I'll get a 9 times 3. 27 minus 12 is positive. So we have increasing, decreasing, decreasing, increasing. So we have a maximum at x equal negative 8 and a minimum at x equal 8. Notice that 0 is not a maximum nor a minimum. And if I substitute negative 8 in there, I'm looking at the cube root of 8, which is negative 2. Negative 2 times negative 36 is 72. 72 minus 24, what would that be? 24 48. And if I put the 8 in there, that will be positive 24 minus 72. Those don't always match, but there it is. Now, another thing that we need to get out of the way is this idea of absolute maximum, absolute minimum. So calculus allows you to find the relative, which are inside of the interval. We have an absolute value, absolute maximum, if the y value is the biggest. I'm talking about this. Absolute maximum if the y value is the biggest on some interval. And we have an absolute minimum if the y value is the smallest on some interval. Notice there was no interval given on number 2, number 6, or number 12. But when I look at the next two problems, I notice that they both have an interval. They're both limited. So I could plug in 0, I could plug in 1, so I could start by saying, well, let's see, what's f of 0? F of 0 is negative 3. How about f of 1? F of 1 is 1 minus 2 minus 3. That's a negative 4. Alright, so far I have this being the lowest point and this being the highest point. But between, I need to take a derivative and figure out if it has a relative maximum, relative minimum. The relative maximum, relative minimum is inside of this interval. I'm only looking at this interval between 0 and 1. So if I take a derivative, that's 2x minus 2 equal to 0. That's when x equal a 1. So if I do my testing, there's 1, there's a derivative, and there's f. If I pick a point to the left of 1, say 1/2. 2 times a half, or 0. 0 minus 2 is negative. If I pick a point to the right of 1, even though the interval is not there, so this point is really not going to help me much. But let's say I pick 2. 4 minus 2 is positive. This function is decreasing, then increasing. So, do you notice the only critical number is x equal 1? And f of 1, I already have to be negative 4. Since I only have two values, I would say the absolute max and absolute min. Absolute maximum, the highest of those two is a negative 3, and the lowest of those is a negative 4, and there it is, I'm done. If I had other values, I would have matched. The highest of all the y values would be the absolute maximum, and the lowest of the y values will be the absolute minimum. Here's another problem. If I figure out what f of 3 is, f of 3 is 3 over 3 minus 2, which is 3. F of 5, 5 over 5 minus 2 is 5/3. So this is 1 2/3, 1.6. So far, this is the absolute maximum, this is the absolute minimum, but I need to know if there are any relative maximums or minimums. Endpoints don't do it. Calculus is the only way to figure it out. I take a derivative of the top times the bottom, minus the top times the derivative of the bottom, all over the bottom squared. So this derivative is actually t minus 2 minus t over t minus 2 squared. Those cancel out. H prime is actually negative 2 over t minus 2 squared. And from this, I'm getting there is a critical number of t equal 2, because that's where the derivative does not exist, and it can never equal 0. So only one point in critical number, and that is, I only have one critical number, I should say, and that critical number happened to be at 2, which is inside of the interval, which is allowed. Here's the derivative, here's h. I pick a point to the left of 2, let's say 0. The top is negative because it's negative 2. The bottom, 0 minus 2, if it's squared, it's always a positive. Negative over a positive is a negative. And if I pick a point to the right of 2, let's say 3. The top is a negative 2, it's always negative. 3 minus 2 is positive 1 squared, that's a positive. That's a negative. So this happened to be decreasing, then decreasing. That means this critical number doesn't apply. Otherwise, I would have had to figure out what that value is and state the maximum and minimum. The absolute maximum in this case is the highest y value, and the absolute minimum in this case is the lowest. since 3 is the highest and 5/3 is the lowest, I end up with those two values. The homework is on page 184. You're going to do numbers 1, 5, 11, 19, 21, 25, and 47. Now, when we start looking at the next sections, 3, 3, 3, 5, 3, and move on, we will practice this over and over, and you'll see this more than enough times.